Today we're going to be talking about an idea called optimization, which is pretty much getting the most for the least, or minimizing the amount of cardboard it takes to make a box, or minimizing the amount of material it takes to hold a certain amount of liquid, something along those lines. So, there are some steps to do this. Understand the problem, which might take reading it multiple times, sometimes more than once. Secondly, develop a math model of the problem. Draw a picture if you need to. Label parts. Give variable values to things that are not labeled that you will need to use. Thirdly, graph the function. Take the domain into consideration. Identify critical points and endpoints. Remember that these come from the derivative. Solve the math model and interpret the solution. So make a statement about what you found. So, first one says, find two numbers whose sum is 20 and whose product is as large as possible. Find two numbers whose sum is 20 and whose product is as large as possible. So, we don't know these two numbers. Let's call them x and y. We know x plus y equals 20. And we know the product would be x, y. We also know that we can't derive something that has more than one variable unless we do it implicitly, and that's going to cause a lot of complications. It would be nice if we could get this product function in one variable. So, I'm going to solve for y, and I'm going to make our product x instead of y. I'm going to put what y equals, that 20 minus x. So our product is 20x minus x squared. Now, if we're going to maximize something, we need to get the derivative and find where it changes from positive to negative. So, let's talk about this. P prime would be 20 minus 2x. Set that equal to 0. And x is 10. Now, on our number line, we know we're going to have to put 10. But you also have to think about that this number could be as small as 0, x, because x plus 0 plus 20 would give us 20, so x could be 0, or it could be as high as 20. If we test a 5 in our 20 minus 2x, we get a positive number. If we test a 12 in our 20 minus 2x, we get a negative number. To find a maximum, because we're trying to find as large as possible, means we need a max. That occurs when our first derivative changes from positive to negative, which means it's going to happen when x is 10, which means y, which is 20 minus x, is also going to be 10. So, 10 and 10 would be your best bet for a product as large as possible. Number 2, what's the smallest perimeter possible for a rectangle whose area is 16 inches squared? Well, we have a rectangle. And I'm going to call the dimensions x and y. We know the area is 16, but we are trying to find the smallest perimeter possible. We want to minimize the perimeter, and the perimeter would be 2x plus 2y. If we look at this and we solve it, I'm going to solve for y again. We get 16 over x. So our perimeter is really 2x plus 2 times 16 over x, or 2x plus 32x to the negative 1. We need p prime, which would be 2 minus 32x to the negative 2, or 2 minus 32 over x squared. So far, so good. Find our critical values. We find out that this equals 0. I'm going to multiply through by x squared, so 2x squared minus 32 equals 0. Pull out a 2. We get x squared minus 16 equals 0, which is x plus 4 and x minus 4. So we get x equals 4 and x equals negative 4. We don't need the negative 4. You can't have a negative dimension on a rectangle, but we do need a 4. Now let's talk about the smallest or biggest x could be. X could be just above 0 and still be a rectangle. If y was just above 0, like 0.1, x would have to be really long. So it actually could be very large depending on how small of a fraction our x value is. So that's our number line. If we test a 2 in our derivative, here or here, we get a negative. If we test a 3, or a 5, we get a positive. So our minimum is going to occur when x is 4, which means y is also 4. No, they won't always be the same, but that's something to think about it. So your statement for this one could be the smallest perimeter possible for a rectangle with area of 16 inches squared occurs when x is 4 and y is 4, or when it's a square with a side length of 4. Next one, a rectangular plot of farmland will be bounded on one side by a river and on the other side by a single-strand electric fence with 800 meters of wire at your disposal. What's the largest area you can make and what are its dimensions? So we have a river, that's water. We have a fence, it's a rectangular pen that's bounded on one side by the river. I'm going to call this x and these two y. And I know I have 800 meters of wire for this electric fence. So x plus 2y has to equal 800. Now, at this point, what do they want us to do? Well, they want us to find the largest area. Well, area is x times y, or if I solve this for x, just because that's the easiest one to solve for, it's really 800 minus 2y times y. So area is 800y minus 2y squared, which makes a prime 800 minus 4y, set it equal to 0, and y is 200. So on a number line, let's talk about what y can be. Y can be as small as 0, and as large as really extremely large, because x could be a small decimal, but realistically, we can't really name a number. It does need to be wide enough to fit an animal of some sort, I think, or to grow things. Yeah, I don't know if it's going to be a pen for animals or if they're just fencing in their farm land. So we need to put the 200 on our number line. If we test both sides of this number line, we get a positive and then a negative. We're trying to find the maximum area, therefore we want where it changes from positive to negative. So that's going to happen when y is 200 and x is equal to 800 minus 2y, which makes our x 400. So a y value of 200 and an x value of 400, those are meters. And our statement could be the maximum area attained using 800 meters of wire to make a rectangle with the river as one side of the rectangle has dimensions of 200 meters by 400 meters. Now this last one you've seen many times in pre-calc. It says an open top box is to be made by cutting congruent squares of side length x from the corners of a 20-inch by 25-inch sheet of tin and bending up the sides. How large should the squares be made to make the box hold as much as possible? So, we've got this box that is 20 by 25, and we are trying to find how large the squares could be to hold as much as possible. We're trying to find the maximum volume. Each little square they're cutting out is x by x. So our volume is going to be our length times our width times our height. Our length is this. Used to be 25, but they subtracted an x from each side. So now it's 25 minus 2x. Our width used to be 20, but they cut an x off of each end. So now it's 20 minus 2x. And our height is going to be this little flap as it stands up. Any of these lengths, which are x. Go ahead and finish this up. Find the maximum volume. Boil that together. Derive. Make your number line. Make sure you write your statement, and we will talk about the remainder of this example tomorrow.